G'day. Copy the heading down and then we'll do some hard yakka. We will start by testing your knowledge, so put down the numbers 1 to 10 under your heading. Question 1. How many columns or groups were there in Dmitry Mendeleev's primitive periodic table? Question 2. Which are the most common? Metal elements, non-metal elements, or semi-metals? Question 3. What is the lightest element that makes up most of the universe? Question 4. What group 2 metal is needed by animals to make teeth, bones and shells? Question 5. What group 2 metal is needed by plants to make their green chlorophyll? Question 6. What common chemical compound reacts explosively with group 1 metals? Question 7. Which radioactive group 2 metal was discovered by Marie and Pierre Curie? Question 8. Do you tend to find metals on the left or right of the periodic table? Question 9. What is the colour of Group 1 and Group 2 metals? Question 10. An old way of measuring valence or combining power was to count the number of hydrogens or chlorine that the element combines with. So what is the valence of calcium in this chemical? Pythagoras of Samos founded a religious movement who believed that the essence of the universe and people is based on numbers. The early teachings of his mathematikoi, or mathematicians, had a profound effect on the early Greek philosophers, as well as the emerging Hebrew, Christian, and Islamic religious traditions. Number has been found to be a fundamental part of a human being. Each person is an expression of a particular 4-number DNA code found in the nuclei of most of our cells. Indeed, we have an obligation to avoid damaging our DNA so that the next generation does not suffer. But number is just as important in defining element atoms. Each atom has a particular number of protons, read from left to right and down the periodic table. Hydrogen has 1 positive proton balanced by 1 negative electron. Uranium, the heaviest natural element, has 92 of each. But the world of chemistry is largely about electrons doing things. And electrons have a wonderful mathematics of their own. So far you have learned that electrons occupy main shells at specific distances out from the nucleus. This diagram shows element 17, which is the nonmetal chlorine. It has 2 electrons in the first main shell, 8 in the second main shell, and 7 in the third. But the main shells can be split into subshells, which have different shapes. This clever mathematician, called Erwin Schrödinger, was the first to work out the subshell shapes. The shapes are S for spherical, P for pear-shaped, D for dumbbell-shaped, and F for freaky. Now the amazing maths. S subshells have 2 electrons. P subshells have 6 electrons. Can you guess what D and F subshells have? The answers are 10 and 14. Each subshell has 4 more than its predecessor. The main shells then look like a pyramid, with more electrons and subshells as you go out from the nucleus. The modern periodic table contains 4 blocks of elements: the S block, P block, D block, and F block. The element block tells you which type of outer subshell an element is filling. For instance, carbon is element number 6. It has filled its 1s and 2s subshells and is starting to fill its 2p subshell. It is a P block element and part of group or column number 4. To make our element boxes larger, most books chop out the F block elements and place them at the bottom. We are going to look at some D block elements, so copy that heading down. We will look at some of the properties of the D block elements and write them down in point form. First, they are often called the transition metals. you will notice that the periodic table looks like a lopsided bridge with an anorexic pylon on the left and Fat Albert on the right. The transition metals link the two tall bridge pylons. The second point is that most transition metals have variable valencies. This is caused by the fact that their outer S and D subshells are very close together. This allows the outer electrons to switch positions easily. This table shows you the variability. Scandium has a single valence of 3 and zinc has a single valence of 2. But manganese sits in the middle of the D block and has a valence of 2, 3, 4, 5, 6 or 7. The third point about these transition metals is that many of their compounds are coloured. Our ancestors were attracted to these pretty chemicals and used them as paints, makeup and jewellery, even though some were poisonous. Put a heading "Some Transition Metals" and include our first metal, titanium. For each metal we will tell you some stories, then we will give you a summary to copy at the end. Martin Heinrich Klaproth was the gentleman who in 1791 invented the name titanium in honour of a pretty ferocious pack of ancient Greek gods called the Titans. Most Aussies love the beach, and you will be familiar with this mineral called quartz or silicon dioxide. It is 2.6 times as dense as water, which is why it sinks in water unless the waves are really pounding. Sometimes in the old sand dune layers, you will find some heavy minerals which are twice as dense as normal sand and usually black. Waves can concentrate the black sands by washing away the lighter quartz grains. The two valuable titanium minerals in beach sands are called rutile and ilmenite. It is natural that the mining companies would be attracted to these deposits, and many dunes along our east coast have had their vegetation removed and the minerals separated. It poses a problem, as beaches need their dunes to be held together by plants, or the sand will be washed away and out to sea in winter. There are a variety of species that do this, from colourful pigface to tall banksia trees. Volunteers have fenced off our dunes and replanted them with native species. Unfortunately, this South African plant called bitu bush was introduced by the sand miners and is now a feral pest. But titanium itself is a wonderful metal with growing uses. It is the 9th most abundant element in nature and is corrosion resistant, lightweight, and as strong as the heaviest steel. The metal is widely used in aircraft bodies and engines, such as this new Airbus, in spacecraft, deep diving Russian submarines, watches and spectacles. Brilliant white titanium oxide has replaced poisonous lead chemicals in house paint and is replacing zinc oxide in high protection ultraviolet sunblocks. The next chosen transition metal is element number 24, chromium, so copy its heading. Tasmanian girl Mary Donaldson became a princess when she married the dashing Crown Prince Frederick of Denmark in a much televised royal wedding. The Tasmanian government looked for suitable gifts to present to the royal couple. One of their choices was a sample of a colourful lead chromate mineral mined in Tasmania and called crocoite. This particular chemical can be purified to a brilliant yellow pigment used by painters such as Van Gogh and called chrome yellow. Chromium presents a range of colourful compounds and a wide range of valencies. 3 is its most stable valence and 6 is its most reactive valence. This is stable chromium 3 oxide and is used by artists under the name chrome green. This chromium 6 oxide is most dangerous and produces chromic acid with water that will dissolve most things, including you. These related chemicals should be handled with all the safety gear and have damaged the lungs of many electroplating workers. But chromium is a metal that we humans greatly value. Its main ore is black chromite, which is iron chromate. It is found in some very dark igneous rocks, with the main deposits in South Africa. For centuries, steel makers have searched for ways of preventing steel from rusting. This picture is from the Manly Wharf. The big breakthroughs came 100 years ago when the British Sheffield steelmakers and the German Krupp engineers began adding chromium to the iron. In 1908, the wealthy Bertha Krupp presented the first stainless steel yacht to her husband, Count von Bohlen und Halbach, as a wedding present. Bertha's name was later applied to these Krupp appliances by some young Australians who were sightseeing in Europe a decade later. Chromium does rust, but in stainless steel it forms a thin oxide coating on the surface of the iron to protect it. The people at Sheffield became famous for their stainless steel cutlery. Chromium is now used in some young men's toys, rich girls' toys, and various tools and spanners. Copy down the next metal heading, manganese. Australia is the third largest producer of manganese ore in the world, with mines at Port Hedland, West Australia, and Groote Eylandt and Bootu Creek in the Northern Territory. The two main manganese minerals are pyrolusite, or manganese 4 oxide, and the pretty pink manganese 2 carbonate called rhodochrosite. The Aussie ore minerals usually look dull, boring black, but one form grows crystals that are called dendrites and look for all the world like plant fossils. These minerals are common in the Sydney Basin. This example I photographed at Gary Beach in the Royal National Park. Manganese is a grey-white hard metal, not unlike iron, and most of its oxide ore is used in steel making in blast furnaces to improve the toughness of the metal. Manganese dioxide is used in normal ever-ready zinc batteries and in the longer life alkaline cells. Manganese compounds have a number of pretty colours depending on the valence. Valence 2 manganese compounds are soft pink in colour. Valence 4, brown or black. 6, green. And the most reactive 7, purple. The human body contains a small amount of manganese and it is needed by plants, so it is a chemical of life. Manganese dioxide was one of my favourite chemicals because it is a catalyst speeding up normally slow reactions. Hydrogen peroxide is kept in dark glass to slow down its normal breakup to water and oxygen. Add the catalyst manganese dioxide and the oxygen leaves far more quickly. Then you can burn things in the oxygen. Potassium permanganate is more dangerous. You should keep it away from strong acids and things that can burn. It is still used in medicine to kill bacteria in nasty ulcers like this one. There are some interesting reactions under strict supervision with proper safety gear. Our next metal is element 26, iron. Copy that down. Iron is the most abundant element on Earth and the fourth most abundant in the Earth's crust. It is natural that this metal, in spite of its many flaws, would be our most used metal in ships, bridges, and in our tall buildings. There are 4 main iron minerals which are distinguished by the streak they leave on unglazed porcelain. They are magnetic iron ore or magnetite with a black streak, hematite, the most used ore with a cherry red streak, limonite with a yellow-brown streak, and pyrite or fool's gold with a green-black streak. Australia has the biggest and purest hematite deposits in the world, centred on the Pilbara region of West Australia. We use the biggest trucks, the longest trains and the biggest ships in the world to export it. We are not certain why so much iron was formed in our old rocks between 3 billion and 1.8 billion years ago. The rocks have tiny bands of iron ore. We think that the oceans were acid and full of dissolved valence 2 iron. Then primitive bacteria appeared which released much oxygen and caused the red valence 3 ore to settle out. We are just beginning to study these primitive bacteria, which are still quite common today. The making of iron and steel in furnaces has been practiced for nearly 4,000 years. The main reaction involves the use of carbon to draw out the oxygen in the iron ore and leaving pure iron behind. The waste byproduct is carbon dioxide. The raw materials used are iron ore, usually hematite, as the source of iron, coal to attract the oxygen, and limestone to combine with impurities in the ore. Air is often blown into the furnace to burn most of the carbon. Here is an empty furnace, and this one is full and hot. These special bricklayers are constructing a new furnace. The process begins when coal is cooked in coke ovens to remove sulphur, phosphorus and nitrogen impurities. The hot carbon coke is pushed out and quenched. The carbon-rich coke is mixed with iron ore and limestone in the furnace. The limestone combines with silica and other impurities in a surface layer called slag. This molten rock can be poured off and used as road metal. The molten iron left can be poured into casting moulds or poured into special containers called pigs. The pig iron is usually remelted to form steels or other forms of iron. This often occurs in electric arc furnaces. The properties of the product depend on the other elements that alloy with the iron and the cooling history of the iron. Cast iron was the original form of iron made. It has more than 2% carbon, which reduces the melting point of the iron by over 200 degrees Celsius. It is very strong but brittle and can be sharpened to an edge. The cast iron is cooled into moulds. Wrought iron was an old and pure form of iron, little made today. It contains very little carbon, but does have slag impurities. It was tough, malleable, and easily welded. The blacksmiths used it to make gates, rails, rivets, and chains. Most iron today is sold as carbon steel, which has less than 2% carbon. As the carbon content increases, the steel becomes harder and more brittle. The addition of other elements change the properties. If you want a high-speed hard drill, you add tungsten or molybdenum to the iron. Stainless steel contains over 12% chromium, which protects it from rusting with an oxide coating. Other metals, such as nickel, can be added depending on the use for the stainless steel. The problem for iron is that of fast corrosion in the presence of air, water and salts. One way of protecting steel food cans is to cover them in tin plate. As long as the tin is not scratched, the tin will block out the air. We no longer make tin plate in Australia. Another method of protection, not used for food, is that of hot dip galvanizing, where the iron is covered with a layer of molten zinc. The zinc rusts first. You may just be able to see the white zinc oxide rust spots. The zinc does not last forever. We galvanise car bodies, pipes and wire in our Newcastle plants. Our Wollongong plant galvanises sheet metal. They also specialise in colour bond sheeting, where the steel is coated in molten zinc and aluminium, plus a tough paint. They even coat steel beams for use in housing. Australia has a need for steel. It makes no environmental sense to close these plants down and make extra greenhouse gases as we import steel from other countries. Iron has a vital role to play in humans, because we need iron to survive. Human blood consists of a straw-coloured liquid called blood plasma, with living blood cells floating in it. Most of those cells are red ones, and their job is to carry oxygen from the lungs to all the living cells in the body. Red blood cells are made in bone marrow. They lead a tough life and are eventually damaged by being rammed under pressure through the blood vessels. This is a cross-section of lung tissue. You can see the ragged air sacs called alveoli. At the top right is the tiniest of blood vessels called a capillary. Red blood cells in these capillaries absorb the oxygen. There are 5 million red blood cells in a single drop of human blood. So where does iron come into the picture? Red cells contain 35% of a reddish protein called hemoglobin. At the centre of each hemoglobin molecule is an iron atom. To replace our worn-out hemoglobin, our bodies need a constant supply of iron. Green vegetables such as legumes and broccoli are one source, but the best source of iron is animal blood found in red meat and fish. Without iron, we become anemic. Our cells look like this, and we feel very tired and cranky. If we carry a child, they suffer too. Chemicals can affect hemoglobin by blocking the oxygen. Cyanide kills, as can rotten egg gas. 0.1% carbon monoxide in the air is lethal. So avoid cigarettes, car exhausts, truck exhausts, running cars in garages, and Sydney's tunnels and ventilation stacks. Another feature of iron minerals is their presence in what scientists call acid sulfate soils. At the end of the Ice Age, the sea level rose and covered Australia's coastal vegetation with swampy water. Swamp water and soil covered by concrete lacks oxygen. Old microbes appear and make iron sulfide. Such ground is common in mangrove areas and areas covered in casuarina vegetation. Ancient coal seams also formed in swamps and contain these iron sulfide or pyrite minerals. The problem arises when you dig trenches to drain the water from the swampy soils. The pyrite reacts with the oxygen, making quite strong sulfuric acid. If you build on the soils, the acid will attack any iron in the building and rot your foundations. Acid runs off the land after rain, killing fish and prawns in the local waterway. So do not build on or drain this sort of land, or you will ruin your house and the local river. 100-year-old abandoned coal mines are still leaking acid. That is why we are training environmental engineers, and they need to be listened to. So copy that one down, Boris. Until next time, hooroo!